All right, guys. Hopefully, this has started up. Let's go ahead and pray, and then we'll get started on today's lecture. We're going to finish up this chapter, which means that we only have two chapters. Uh, well, no, I'd have to look. I think we only have two chapters remaining in the unit. I could be wrong, but I think that's it. And now, granted, these have been pretty lengthy chapters, so who knows how many modules that is. I think this last one here is 4 or 5 modules. So, depending on what it is, we might finish up this week though, and then we'll have some time maybe for some review, and definitely, or maybe some labs even that I could send home to you guys. That would be really really neat. Let's bow with me if you could as we go to the Lord. Lord God, I just ask that you be with those that are watching today, be with those that aren't. Lord, help us through this strange time as we continue to kind of live through isolation a little bit. While other states are opening up, we're still isolated, Lord. And I just pray that we find comfort and solace in you and all that you are. In Jesus' name I pray. Amen. All right, so today, like I said, I want to finish this chapter up, which means we have a few more slides. There's only about 6, to be honest with you, but we have a few more slides than I wanted to have. But that's all right. Sometimes you got to press through. And I wanted to start off, we're talking about air pollution. And we mentioned photochemical smog and acid rain in previous slides, but we didn't go into detail as to what each one of these things really relate to. So smog was originally just water vapor, so fog mixed with smoke. That's why you get the idea of smog, smoke and fog. That was back when most of the time when that word was first coined. That's when we were using fire, wood combustion as our primary fuel source for most things. Some people still use that. I don't know. Maybe somebody in this class has a wood burning stove that they use to heat their home, or maybe even cook with. I don't know. Some people still do that. So this isn't a crazy concept, but today's smog, or modern smog, if you will, is a little bit different. It's really more of a mixture of sunlight, water, and VOCs. For those of you who don't remember what VOC is, that is volatile organic compounds. So these are things that have long carbon chains that evaporate at room temperature. Okay, so or even just ambient temperature, whatever it might be. So things like gasoline. The reason that if you have an open container of gasoline, you smell it, okay, from a pretty good distance, is because it's a volatile organic compound. It vaporizes almost on contact of any surface, which actually makes it to be a really good fuel, because we need it to vaporize. We need to spray it into a cylinder head and it form a vapor, because a vapor burns much more regularly than liquid gas. Contrary to popular belief, and don't go home and test this, but something like gasoline, if you have a bucket of gasoline and you drop a match in it, especially if you have just poured it in there, it's probably not going to light. Now, again, don't test this, please. But it's probably not going to light, and that's because the match is going to go directly into the liquid, and it's going to go out. It's going to extinguish. What causes gasoline to ignite is the vapor coming off of it. So if you take that same match, if you put that bucket of gasoline or whatever you have out in the sun for a little bit, and you allow it, give it just 30 seconds, you allow it to kind of heat up a little bit and the vapors to start coming off of it, you can then put a lighter next to it, and the vapor will ignite. Again, a bucket of gasoline is a lot of energy. Do not do that by any means. But it's the vapor that's burning, not the gas itself, not the liquid gas. So VOCs mixed with water, which we have obviously in the atmosphere, those are called clouds. We have lots of water in the atmosphere, and sunlight forms this photochemical smog, which has a drastic effect. We have a really damning picture here, and there's lots of these pictures on the internet. I don't know what city this is, but you can see that here's a clear day, maybe like a day that they're having now because smog levels are down so much around the world, and there's a day to the left there that is a day filled with smog. Obviously drastic effects, drastic differences between those two. It's quite a dichotomy. So the process of forming these photochemical compounds is really, it starts with nitrogen dioxide. Now, you'll notice that there's a trend here. When I talk about air pollution, I'm talking about nitrogen dioxide and sulfur dioxide. Those are the two common ones. And again, when we think of air pollution, when I think of it, I think of carbon dioxide. But carbon dioxide has very little health. It causes very little health issues. Okay, I mean, and think about that. That should make sense. Carbon dioxide, we drink it. I drink carbonated water all the time. You guys drink soda all the time. So CO2 is abundant and it's around us, and we even ingest it. So it doesn't really affect our health. The reason CO2 gets a lot of attention now is because of global warming, which we talked about actually a few chapters ago. It was like the last thing that I got to before we switched to, because it was like Unit 9 or something. And it has a drastic impact, and it is changing our lives for the worse because we're pumping so much CO2 in the air. But when we were first, when we think about human health and the health of organisms, CO2 really doesn't have a drastic impact. In fact, like I said, we can ingest it and it doesn't do anything. Plant life relies on it. So obviously, CO2 is not bad. It's not a bad thing. But as you guys have probably heard before, everything in moderation. Everything can be bad. It doesn't matter what it is. Apples can be bad if you eat too many of them. Okay, the apple seeds contain arsenic. You can actually die from eating too many apple seeds. So if you're eating an apple, you might ingest an apple seed. You're not going to die. But if you eat, 500 apples, and you ingest an apple seed from each one of those, you probably would contain enough arsenic to kill you. So everything in moderation. CO2, if it is left unchecked and it's able to accumulate in the atmosphere over many, many years, and the parts per million or billion or whatever it might be, or whatever unit of measure you're using, it just continues to climb. Obviously, then we're going to have greenhouse gas effects, and that's going to affect the global temperature of the Earth and thus our survival. So, however, nitrogen dioxide and sulfur dioxide form things that are bad for us. VOCs, or again, volatile organic compounds, take up more of the nitrogen oxide, stopping it from forming bonds with ozone. That should be ozone, not OZPNE, sorry. So what's happening is nitrogen will kind of cycle through, and we're going to talk about cycling a lot today. It's going to cycle through in the form of nitrogen monoxide and nitrogen dioxide. Nitrogen monoxide, monoxide. I'm sorry. Yeah, it's NO, so that's fine. Mono obviously meaning one, but nitrogen monoxide is not very bad for you. It's one of the least of the nitrogen oxides as a pollutant. It's still bad, but it's not as bad as nitrogen dioxide. So as these two things, they kind of shift, they cycle in between an NO and an NO2. But what VOCs do, these volatile compounds, is they come in and they attach to a nitrogen, stopping them from forming bonds with ozone. So it creates more ozone in the process, and it creates these long carbon chains connected to a nitrogen atom, which are more harmful as not only a pollutant, but also as a greenhouse gas. So one, it enables the creation of more ozone, which is a horrible greenhouse gas and a very bad pollutant, smells really bad too. And it stops this natural cycle of nitrogen oxide and nitrogen dioxide and creates more of these nitrogen photochemicals that are attached to these volatile compounds. So it's just not a good thing. And that results in more smog. Now, temperature has a lot to do with this as well. And that's not just a global warming kind of thing, but smog in particular is tied to temperature. And what I mean by that is tied specifically to thermal inversion, which is when a warm layer of air at mid-altitude, so somewhere sort of in the middle of the troposphere, covers a layer of cold, dense air below it. Okay, so we have this cold air that's trapped by a layer of warm air, and then on the top of that you have cold air again. It kind of acts as this insulating layer, and what that does is it stops the air at the bottom from warming up, that smog layered air, that air with the most pollutants because it's the closest to the Earth's surface. It stops it from continuing to rise and thus cleaning out all those pollutants, allowing them to to diffuse out into the upper atmosphere. So instead, it concentrates it. And you guys can see that. I don't know if the camera's picking it up, but here we have two lines of smog of all of these different pollutants that are trapped at surface level. Okay, and that's why smog can be so deadly, because as it gets trapped there, and if you continue to pollute that day or that week, that smog just condenses, and you get more and more pollutants in a confined area. And that parts per billion or parts per million, whatever you're looking at, it just grows and grows and grows to the point where you walk out into an area like that and you're trying to breathe, because this is where people live. Okay. Those cities down there, you can't even tell that one is a city, but the one on the right, you can still see the city. There's millions of people living there. Okay, cities are called that because of the population. So there's millions of people living there, and they are trapped in this haze of smog that it's not going to leave because of thermal inversion. So that smog can produce acid rain, again, in the two forms when we have those nitrogen oxides and that sulfuric acid, or excuse me, those nitrogen oxides and that sulfur dioxide. Those can both form a secondary pollutant through a little bit of chemical conversion in the atmosphere to form nitric acid and sulfuric acid. Both of those are pretty devastating acids if you've ever used them in Mr. Walters' class. I don't let my physical science class use them because I wouldn't trust them with acid, at least not like that. Maybe some acetic acid, something like vinegar. But when we talk about nitric acid or sulfuric acid, we're talking about really high concentrations usually. You can dilute those down, but still relatively high. So even in low doses, which don't get me wrong, we're not talking about high concentrations here, big molarities. We're talking about small concentrations in the atmosphere. But even in small doses, things like limestone or calcium carbonate, or in the case to your right here, in this picture, we have a marble statue, which is made of calcium carbonate as well. They're going to have drastic effects. If sulfuric acid rains down in the form of acid rain, which is what usually happens, things like these beautiful statues that are outside are going to sustain acid damage. Now, you don't hear about this that much anymore. In the early 90s, this was a big concern. That's when we started to change the way that we did things. And really what we did is we changed the way cars produced sulfur or sulfuric gas or nitrogen gas in the form of nitrogen oxides or sulfur dioxide. So we altered that to stop this. And it actually has worked out fairly well. And we're going to talk about some of the things that we did to try and produce less of these nitrogen oxides and the sulfuric dioxide. But you can see the effects. Like I said, if we continued to let it go for the last 20 years, actually 30 years, we would see a lot more of this sort of devastating effect where marble statues wouldn't exist. But listen, I know what you're sitting there thinking, who cares about marble statues? The environment is much more impacted. So here we have an example of a strip of forest. The forested areas were getting these scars, which were these sort of lump areas where trees were dying off. And we attributed it to acid rain. What would happen is acid precipitation would fall, causing the soil to become more acidic. The trees could no longer grow in those areas. You would get lakes, which obviously are susceptible. Any sort of waterway is susceptible to this, because what happens to that sulfuric acid-laced rain? It finds the lowest point, which is usually a lake or a river. It bioaccumulates that acid there. And so you get massive die-offs of organisms in all of those ecosystems in any sort of waterway. So that was really the effect. And what's interesting, what is crazy about this, is that this is pollution that would start off in a city not unlike one of these cities here, and then that acid would accumulate in the atmosphere and it would fall somewhere else outside of the city, devastating a relatively pollution-free area. So clouds don't stay in one place. Or moisture that forms in one place often falls in another. Okay, so you get moisture that would form in above these cities, and form these acidic compounds. and then it would fall onto other areas that didn't have anything to do with the pollution. Don't get me wrong, you get acid rain in the cities as well, but a lot of times, like I said, you'd have this casualty almost where these forested areas, these very nice ecosystems, would be devastated by this acid rain, and they had nothing to do with the creation of it. So what are some of the things that we've done? Well, the best way to fight pollution is to not generate it in the first place. Okay, so what we've done is we've taken, to address the sulfur dioxide, we've taken things like high sulfur coal and we've said we're not going to burn it anymore. Okay, so that's one of the problems with Illinois coal. One of the reasons that we use a lot of nuclear power is because while we have a ton of coal, a lot of our coal is sulfur heavy. It has a lot of sulfur in it. So we try not to burn it as much as we can. Now that doesn't mean that we don't have coal-powered plants. We absolutely do. And we deal with the consequence of that. But a lot of times we'll even outsource our coal to from other places where there's a less of a sulfur density to it. Again, Illinois has what's considered dirty coal. So we have limited the use of sulfur coal or sulfur-containing coal and sulfur-containing fuels. Again, diesel just 20, 30 years ago used to have a very high amount of sulfur in it. Now you can only buy low sulfur diesel, and that is through regulations. We've just put things in place that have made manufacturers produce fuels that contain less sulfur. So we also have gotten better with the air fuel mixtures that we use in our vehicles. One of the big things that contributes to that is the abandonment of carburetors in automobiles, and the acceptance of fuel injectors. Wow, kind of evaded me there for a moment. So fuel injectors are able to mitigate some of the downfalls of carburetors in the fact that they produce a much better fuel-to-air mixture for the vehicle, so that it can create the combustion that it needs, burn off as much fuel as possible, converting all of that fuel to carbon dioxide and water vapor, as opposed to leaving some of that fuel out and then allowing that volatile compound to go into the atmosphere. So we've changed that. Both of those things have lowered the amount of sulfur dioxide and nitrogen oxides in the atmosphere quite a bit. There's other things that we've done. We've tried to lower the temperature of certain reactions, especially in industry, if we can do it, because less temperature means fewer nitrogen oxides. We have introduced catalytic converters, I think since the 90s. Could be wrong there, maybe the 80s. I don't know. I'm not 100% sure. But catalytic converters use palladium and platinum. That's why some people try to steal them. But they use these two precious metals to capture some of these nitrogen oxides and sulfur dioxides, and even some carbon dioxide for that matter. So they try to lower the emissions of the vehicles. It's basically like a filter that we use. Now, because of that, another thing that's kind of been good for the environment, we've had to switch away from lead-bearing fuels. So we don't use lead-based fuels anymore. There's no lead in our gasoline. Lead used to be used in fuels to help prevent knock. However, we don't use it anymore because, one, lead is a heavy metal, and heavy metal poisoning is a real thing. But also because catalytic converters don't work with it. Lead will coat the palladium and the platinum. So we use gravity filters when we talk about bigger industries. We'll use gravity filters, and we talked about scrubbers when we went to ConocoPhillips. What a scrubber is it's effectively just a shower for the exhaust. So in those smokestacks, a lot of times they will spray water down on the exhaust that is coming off of that smoke, and they'll basically wash it. So if you think about like acid rain falling down from the sky, it's the same sort of thing. What they're doing is they're spraying that exhaust with water, and a lot of the particulates, a lot of the sulfur might mix with the water to form that sulfuric acid, and it will rain down before it ever reaches the atmosphere. And then, of course, the biggest thing that we've probably done is we've just put restrictions on things like emission. Like right now, Chevy or Ford or any of the big players in the automobile industry, they have a certain mile per gallon average that their entire fleet has to reach. Now, that doesn't mean that they can't produce a car that only gets 7 miles per gallon. They can. It's called the Corvette. But if they produce that car, they have to average that with another car that hopefully has a much higher miles per gallon to get an overall average of, I want to say, like 25 miles per gallon. I could be wrong there, for their entire fleet. So you can imagine that if they have some cars that are getting 5 to 15 miles per gallon, that means that they have to have other cars, multiple cars, to make up for that get, 25 to 35, maybe even 40 miles per gallon. All right, so let's talk a little bit about ozone. First thing that I want to remind you guys of, because we talked about this already when we talked about the layers of the Earth, is that ozone in the troposphere is bad. So ozone right here at ground level is not a good thing. Okay, all it is a smelly, harmful gas that produces a lot of greenhouse effect and contributes to global warming horribly. It's also just bad for you to breathe. Lots of bad things. Okay. However, in the stratosphere, it shields against harmful radiation from the sun. So it is literally protecting us in one place in the atmosphere, and it's killing us in another. Okay, so you can imagine, we're going to talk more about the stratospheric ozone, if you will, in this particular little section. So right now we're talking about the good things about ozone. Ozone, by the way, for those of you who don't remember, is O3. Normally, oxygen is a diatomic element, which means that it's O2, usually found in nature. However, in the presence of sunlight, when you have UV radiation, it will split and form O3, which is ozone. Okay, so 3 molecules of oxygen linked together through bonds. And it has unique properties. But first, I want to talk about its creation. So solar radiation strikes the traditional O2, the naturally occurring diatomic oxygen. The diatomic oxygen splits to form free oxygens. Those oxygens encounter another O2 that has not split yet, and ozone is thus formed. Oxygen being very electron hungry. It's an incredibly reactive element right next to fluorine there, and it will readily latch on to another diatomic oxygen to try and form a bond and become more stable. O3 is more stable than just free oxygen, okay, with a negative charge. So the process repeats itself, and it actually produces a cycle. So ozone will be created, and then ozone will break apart, and then it will be created again, and then it will break apart, which means that you have a relatively level amount of ozone in the stratosphere, in this particular layer of the atmosphere at all times. Okay, and that's important because of what ozone does. Well, like I said, we kind of already hit on it. It's not here. I thought I had another thing that kind of highlighted the things that ozone does. Maybe it's the next slide. I don't remember. But ozone, remember what it's doing is it's stopping particular UV radiation. Ozone is such a dense molecule with these heavy oxygens all linked together that UV radiation, UVB in particular, can't penetrate it. Okay. Now, does that mean that if you go to the beach, you're not going to get some UVB? Absolutely, you're going to get some UVB. So put on your sunscreen. Sunscreen is the lesser of two evils. I've known people, I knew a person one time that said they wouldn't use sunscreen because it has a bunch of chemicals in it and it's bad for you. And they're absolutely right. 100%, it is bad for you. You know what's worse for you? Skin cancer. Okay, sometimes you guys have to be discerning. You have to figure out, what's the lesser of two evils in the world. And sadly, that's the case in the form of sunscreen. If you guys are out right now, I went swimming yesterday. It was cold, but I went swimming yesterday. So if you guys have been doing any of that, if you've been out in the sun, maybe working, maybe doing some work around the house, whatever you're doing, use sunscreen because UV radiation is not anything to mess with. It will cause skin damage. It will cause damage to your DNA, and it can very easily cause skin cancer. Okay, especially if you're like me and you're just pasty white. Okay, if you're one of those people that is just translucent like myself, make sure that you guys are wearing plenty of sunscreen to protect against what the ozone layer has not prevented from from escaping, has not stopped from coming down to Earth. So let's talk about its depletion real quick. The reason that there's a whole module basically talking about ozone is because of this right here. For the last, probably 50 years up until the 90s, again, this is when we realized this. The 90s were a very big sort of awakening time where we started to realize there's a lot of environmental issues that we needed to take care of. We realized that refrigerant interfered with the cycle. So CFLs, which are chlorofluorocarbons, weird name, so we just call them CFLs, were used in refrigerant. I don't know about you guys, but maybe some of you have already started flipping on your ACs, okay? I don't know about you, but I bet you most of you like having cold soda and cold food kind of at the ready in your refrigerators. If it wasn't for CFLs and modern refrigerants, really more now than CFLs, but modern refrigerants and the technology that they provide, we wouldn't have cold air. And again, I think most of you guys would be suffering here in just a little bit when we're going to have like 95-degree days. You're going to love your air conditioning during those times. Okay, I do. So we rely on what's called a refrigerant. And that is a gas that has very special properties. It can easily be condensed, so it can be pushed together real close, and then it can easily go back into its gas form. And what happens is when we push something together really close, it usually gets colder. So if you take a gas and you make it a liquid, it cools down. Okay, so that's what your compressor does on your furnace or on your air conditioner rather, or on your refrigerator. You guys have heard those things click on and they kind of make this kind of sound, that humming noise. What that is that's your compressor taking the gas and compressing it back down to a liquid, or at least a more compressed gas. And then it allows that gas to travel up through the refrigerant line, okay, the coolant line. And as it goes through that line, it relaxes and it goes back into its gas form. And when it does that, it takes heat away. Okay, so as it goes through your refrigerator, it's taking heat away from the food and causing that to be cold. There's no such thing as really making something cold. What you do is you take heat away from something and that subsequently becomes cold. Okay, this was not supposed to be a lesson on HVAC technology, but it's important that you guys realize how this works. I just hope you understand how things like that work. So then as it takes that heat, it absorbs that heat away from those objects. Those things become cold and the gas becomes warm and it goes back to the compressor where it compresses again and it becomes cold again. Okay, so interesting. It's just interesting how all that works. And CFLs were one of the type of special material. There's only a few materials that can do this very effectively. CFLs were one of them, and CFLs they didn't catch on fire, and they were readily available. So we thought, and they weren't toxic. Like, you can breathe them in; they're not going to harm you. And so we were like, all right, this is perfect. Okay, it's not going to do anything bad if we put them in a house. Okay, that's what your AC. If you have your AC running right now, that's what it's running with. Okay, not a CFL, but a similar refrigerant. So we were like, this is perfect. What we didn't realize is that as that CFL escapes in the atmosphere, it's a really light gas. That's one of the properties. So it goes all the way up to the highest parts of the atmosphere. And sometimes that happens. You get a leak in your AC system. You have to have it recharged. Trust me, I've done that multiple times with old air conditioning units. So that leak, all that CFL just kind of goes out in the atmosphere. And you're like, oh, it's no big deal. It's not toxic, whatever. It's just cost the homeowner a little bit of money, but that's the only downside. What we didn't know is that CFLs would introduce chlorine to the stratosphere. And for those of you who don't know, chlorine, again, is very close to fluorine. It's super reactive, just like oxygen and fluorine. Super reactive. So it would go up there and it would wreak havoc on that ozone layer. It would steal oxygen in the form, it would produce this Cl minus, and it would steal oxygen away from O2, and it acted as a catalyst. So it didn't ever disappear. Normally in a reaction, like, all the products are used up to make reactants. But in this reaction, and you guys can kind of read through it here, our chlorine never goes away. It just does this process where it makes chlorine monoxide, and then it goes back into chlorine and oxygen, or dioxygen, diatomic oxygen, so O2. So it basically just continues this process, and what it does is it takes ozone, O3, and it changes it to O2. So it just completely destroys any ozone that was there. And so what we started to have is we started to have this hole in the ozone layer. And we started to see that there was areas around the world where the hole was prominent that you'd have a lot more cancer, skin cancer, because of it. You'd have a lot more UVB radiation coming down that was not absorbed by that ozone layer. So this was a really bad thing. The ozone layer was protecting us all this time, and we didn't even realize how beneficial it was until we started to destroy it. CFLs have since been banned. I just got a new air conditioner. It uses a new, Freon is completely outlawed now. You can't buy it anymore in the United States. We don't produce it. Freon used to be the refrigerant of choice, but it was a form of CFL, and it was bad for the environment. So they got rid of it. Now they use, I think it's called radon. I don't remember. It's got a new fancy name, but it's a better refrigerant that doesn't cause as much harm to the ozone layer. And actually, in about 10 years, they're going to replace that. They already have a plan to phase that out. So, last slide right here, indoor air pollution. This is really important. I probably shouldn't have condensed it just down to one slide because this is something that might affect you. I hope that all of your houses have two things installed, okay? A smoke detector. So it doesn't necessarily have to be carbon dioxide, but a smoke detector and carbon monoxide detector, okay? That's just CO, carbon monoxide. Why? Smoke, obviously, for fire. That way, if you're asleep and there's a fire, you can get out. But the carbon monoxide is maybe even more important because carbon monoxide is a colorless, odorless gas. You can't smell it. You can't taste it. It can just be there. And if you get enough of it in a closed-off space like the indoors, like a room, you could die. Not only will you get oxygen deprived, but you'll actually die. Carbon monoxide is probably the most dangerous one on here. Don't get me wrong, asbestos and radon cause cancer. They're not good by any means, but they're just less common, especially nowadays. If you live in a really old house, you need to be concerned about asbestos. If you don't know what asbestos is, it is a fibrous silicate mineral. It's a rock that looks like thread. It's weird like that. Look up pictures of it. It's very strange. And they thought it was a miracle material because it was very flame retardant. That was sort of its claim to fame. It was really good. Flame suits are still made out of asbestos. Okay. However, then they realized many years later, after they put it in pretty much everything, because what's not to do? It's very beneficial for everything that we construct to be flame retardant. To not catch on fire very easily. So we put it in everything. But then we realized that, if that stuff gets in the air, it basically blocks up our alveoli, causing it to be very difficult to breathe, and then it eventually causes cancer, and you die from a very deadly cancer. Not good. So asbestos has thus been banned. But if you have a home that was built, anywhere past probably the 80s, you don't have to worry about asbestos too much. If you're in a building that, like the one that we're in right now, the science building, this is a fairly new building. They did not use asbestos. It's outlawed. Radon is kind of dangerous. It's a radioactive gas that radiates from soils and rocks that are beneath a house. So if you live on a concrete basement, you're fine. But if you live granted, you can have some seepage of radon from that, but still, if you live on a crawl space that's just rock or soil underneath, then you're a little bit more concerned. But some areas don't produce radon, others areas produce it, and there's radon mitigation services that take the radon out of your house. But if you don't do that, if you don't have your house tested, it can cause lung cancer. I believe the book said 14% of all lung cancer cases are from radon. So it's obviously an issue. VOCs, I'm going to get back to carbon monoxide because I just think it's so dangerous. VOCs are also a problem. These are from glues and paints, that you use in households. So even paints that don't have asbestos anymore, they have a lot of these VOCs. That's why paint has that chemical smell, almost like gasoline. After you paint something, you don't want to sleep in that room. We just finished painting a room because a lot of people are painting right now because there's not a lot to do. and we did not sleep in that room for a couple days. It was our master bedroom, and we did that because we were letting it kind of air out from all those volatile compounds. Formaldehyde's a big one. This has hit me personally. I was one of those people. I don't know if you guys remember, man, maybe 5 years ago now. Lumber liquidators. I know you guys are like, what the heck is that? That is a store that sells hardwood and flooring, basically. They got in trouble. They got in a lot of trouble because they were selling Chinese-made laminate flooring that had a lot of formaldehyde in it, and it was dangerous to have in your house. And you think about it, like if you have like one piece of furniture that might have formaldehyde glue or a laminate in it, it's usually the formaldehyde is used in a glue, and then the floor is laminated together, so that means that it's glued together basically. And then you have that formaldehyde that it's constantly basically leaching off or being absorbed into the air around it. So they were selling this product. I actually bought some of it. Not some of it. I bought 1,500 basically square feet of it and laid my entire first house with that flooring. And so I was they sent me a kit to test for the formaldehyde levels in my house. Luckily, it didn't have any, there was no concern. Like there was some formaldehyde, but not nearly enough. I no longer live in that home, but it's still something that haunts them to this day. It was a very big deal at the time. And that's why you need to be careful as to where you produce or where you buy things. And if it has a strong smell to it, leave it outside for a couple days and let it air out because it can be dangerous to your health, especially things that were made with cancer-causing compounds like formaldehyde. Going back to carbon monoxide, I hope you have carbon monoxide detectors in your house. This is really dangerous. Just last year, I believe, and this happens, I'm sure, every single day. There was a couple, actually I think it was an entire family, that accidentally left their car on in the garage. Okay, shut the door and just left it on. I don't know, wasn't thinking. We've all, maybe I'm the only one. I've gotten out of my car with it, or started to get out of my car with it still in drive before. Nothing bad's ever happened. Mistakes are made sometimes with vehicles. So this individual came home from work, left the car on, went inside. The car was running. Cars don't have an automatic switch that shuts them off. So it ran all day or all night. Everyone in that house went to bed with that car running in the garage. They didn't wake up the next morning. Okay, everyone in the house, I think it was 4 people, 2 kids and 2 adults, died. And it was because of carbon monoxide poisoning. They didn't smell it. They didn't know that it was there. But carbon monoxide seeped in from the garage throughout the house, permeated throughout the entire home, and suffocated every one of the kids and the adults. It's a really dangerous thing, and it's something that you guys need to take seriously. If you don't have carbon monoxide detectors, make sure that you get them. Indoor air pollution can, unfortunately, harm you. So I pray that doesn't happen to anyone, obviously, here, and I hope that you guys are all okay. I know that I went long today, guys. But I wanted to finish up this chapter. We will start on the next chapter, which is chapter 16. 16 next time. If you guys are reading along with me, I hope that you are. Actually, I guess we have a reading quiz to get to. So that'll probably be next time or the time after that as well. You guys will have a couple days to get it done, though. So, all right. Nice talking to you. See you next time. Bye.